We're now ready to define the analytic signal. Let's call it Z0 for our simple example. Using the expressions for X0 and Y0 that we found in the previous videos, and Euler's formula, what do we find? Well, Z0, our analytic signal, is equal to our original signal X0 plus I times the Hilbert transform of the signal, which we called Y0. And if we plug in the results that we found for each of these two signals, X0 is 2 times the cosine of omega naught t, plus I times Y0, which we found was 2 times the sine of omega naught t. If we then use Euler's formula to combine these two sinusoids, we'll find that it's equal to 2 times e to the I omega naught t. Now notice what happens here. This analytic signal, Z0, contains no negative frequencies. As we mentioned before, the effect of the Hilbert transform is to eliminate the negative frequencies from X. The spectrum of this new signal, Z0, consists of a single peak at omega naught, compared to the 2 peaks at plus or minus omega naught in the original signal, X0. In this case, the analytic signal, Z0, is simpler than the original signal, X0. To express the original signal, X0, required 2 complex exponential functions, compared to only 1 complex exponential function required to express the corresponding analytic signal. There's an interesting geometrical interpretation to this. Consider plotting X0 in the complex plane. Because X0 is real, this quantity evolves in time along the real axis. But to keep X0 on the real axis, the 2 complex exponentials that define X0, e to the I omega naught t and e to the minus I omega naught t, rotate in opposite directions along the unit circle. By doing so, the imaginary components of these two vectors cancel, and we're left with the purely real quantity, X0.